Hi guys, we are going to talk about a very useful principle. It is called pigeonhole principle. Some of you may have already heard of it. Here's what it is. Suppose there are 10 pigeons and 9 pigeonholes, like there are 10 pigeons in total, 9 pigeonholes, and we want to place the pigeons back into the pigeonhole. Many possibilities can happen, right? But one thing for sure that must happen is, if one takes each and the 10th one must be placed into one of those which is already occupied by some other pigeon. So in other words, at least one hole must have at least two pigeons. So one hole must have two pigeons. So that's for sure. And now, what if there were 10 pigeons and only 3 holes? Again, there are many possibilities. Several possibilities can happen, but for sure, if we place 3 pigeons in each hole, and the last one, the 10th one, must be in one of those 3, right? That means one hole must have 4 pigeons. So one hole must have 4 pigeons. That's what's gonna happen. So I'm gonna write one hole must have at least, I'm sorry, not just 4, just at least 4 pigeons. Okay, and the above one is one hole must have at least 2 pigeons. Now in general, so let's generalize it. That, by the way, that's basically the pigeonhole principle. So in general, if n pigeons fly into m pigeonholes, assuming number of pigeons is more than the number of pigeonholes, then we can conclude that at least one hole must contain 2 or more pigeons. That means at least 2 pigeons. Well, the proof of this is actually pretty straightforward. Our book just takes it as a principle, that means axiom without proof, but the proof is pretty easy to follow. We can prove this by contradiction. Okay, so if we know that, that means if n is greater than m, then at least one hole must contain 2 or more pigeon. If you remember, how do we negate if then statements? If this is your P, this is your Q, so the negation is P and not Q, right? So let's assume. Here's the outline of the proof. Let's assume, suppose, 2 things that we have to assume. 1, n is greater than m. That means n pigeons is going to fly into m holes. And here the important thing is where n is greater than m. So this is what we assume. Second, that's the if part, right? And then when we prove by contradiction, we want to also assume the negation of that one. At least one hole. That means the negation will be no holes, right? So no holes contain 2 or more pigeons. That means no hole contain more than 1 pigeon. 2 or more, that means more than 1. So no holes contain more than 1 pigeon. Okay. So that's the negation of those these if-then statements. We want to derive a contradiction. So now, no holes contain more than 1 pigeon. This statement number 2 is equivalent. That means, so the 2 implies all holes contain 1 or less pigeons, because no hole contain more than one pigeon, that means all holes contain one or less, right? All holes contain one or less pigeons. Now, how many holes do we have? There are m holes. And then we do know all these m holes contain one or less pigeons. This implies there are no more than, there are m or less, right? M or less pigeons in total. Okay, and now do you see that this is a contradiction, because we say there are n pigeons where n is greater than m. Now we, from the statement number 2, we actually conclude that there are m or less pigeons, which is contradicting to what we are supposed. So this is a contradiction. This contradicts to statement number 1, right? To 1, where there are m pigeons and n is greater than m. So therefore we finish the proof because we reached to a contradiction. Therefore, what we suppose is not right, and the original statement is right. So therefore, pigeonhole principle holds. Well, a generalized version. In fact, if we have m and n where n is greater than m, then we can conclude that at least one hole must contain this ceiling function of n over m or more pigeons. Now this ceiling function is like this. Let's talk about the ceiling function. Ceiling function means the ceiling of x means the least integer greater than or equal to x. So basically, for instance, if you have ceiling function 1.1, then this is going to be 2. By the way, this is different from floor function. Floor function, that's the greatest integer less than or equal to that. You're going to ignore the integral parts. That's equal to 1, right? So this one is actually you're rounding to the next integer. So 1.1, the next integer is 2. And 2 is the smallest integer that's greater than or equal to 1.1. Now, earlier we talked about 10 pigeons into 3 holes. So in this case, n is 10, m is 3. So when you find the ceiling function of 10 over 3, which is 3.3 repeating, you're running to the next integer, which is 4. That's why one hole must contain at least 4 pigeons. Well, the book actually provides another version. This is a function version. This tells us a function from one finite set to a smaller finite set cannot be one-to-one. That means there must be at least 2 elements in the domain that have the same image in the codomain. That means this. Okay, let's visualize that. So suppose you have function f from this domain and to the codomain. And if you have, say, the number of elements here is more than the number of elements in domain is more than the elements in the codomain. So let's say, suppose we have 1, 2, and then say 10, right? And then here you have A, B, and what's the, well, maybe let's use 1 prime to 1 prime, 2 prime, and you have only 5, say 5 prime. Now, these at least, this is saying this cannot be one-to-one because you don't have enough elements in the codomain to be one-to-one. So more than, there has to be some elements in the domain. They will have the same image in codomain. So sometimes they will match to the same elements. They will be mapped to the same elements, right? So this is what the this pigeonhole principle says. In the next video, we are gonna introduce how to use this principle to solve some problems that sometimes can be very difficult to solve.